Hello, welcome to some more chemistry with Mr. Hicks. Today we're going to learn about stoichiometry and percent yield problems. Let's take a look at what we should know by the end of this. What you should be able to do by the end of this is that you should know what it's meant by percent yield when we say this is a percent yield. You should be able to set up and calculate some percent yield problems, and we'll do a couple of examples of those. And then finally, you should be able to offer up some reasons as to why yields are less than 100%. We'll figure that out. Okay, so percent yield is just a ratio of how much product is actually made compared to the theoretical amount of product based upon the conservation of matter. Let's pick this apart a little bit. First of all, it is a percent problem. And so percents are always the part over the whole. So there's a generic formula. It's going to be a part of something divided by the whole of something. We call these ratios. A ratio, when you hear that word, think of it as like a fraction. And so in this fraction, we have part of it that we want to know out of the whole thing, which is something else. Okay? Another thing I want to point out to you is that this is all about the product. So in other stoichiometry problems, you might be calculating how much reactant you need to something. In this type of problem, that is not the case. You're going to be figuring out how much product was actually, theoretically could be made, and then figuring out what percentage of that was actually made. And then finally, we're going to take a look at these two terms here. I got them marked up here, actually or theoretically. And down here you can see here is the formula that we're going to be using for it. And we're going to take percent yield, and we're going to take the actual yield. Again, yield just means product, right? Yield means product. And so we're going to take the actual amount of product that we're going to get. This is normally something that's given in the problem. And then we're going to take that and divide it by the theoretical amount of product we should get. And we find that with stoichiometry. Okay, so stoichiometry is based on the conservation of matter, right? And so with that law, conservation of matter, we should be able to predict how much product we will get from this. So if we don't get 100% exactly, is that defying the law of conservation then? Well, no. Sometimes in many laboratory experiments or many, industrial processes that take place, they might get yields that are greater than 100%. However, these are kind of rare. We'll talk about those. And then there are some reasons for some losses where they would actually get less than 100%. Let's talk about reasons that they may have extra atoms that show up that they weren't counting on. And one of the biggest reasons why is what I call side reactions, okay, or extra reactions that take place. Just like the commercials say, oh, this may have some side effects. Well, a side effect is caused because there's a reaction that's taking place that is not being controlled by maybe your body, if it's something that's part of your body, or by the experimenter, or by the person who's in charge of the industrial processes. Not everything can be controlled. We don't do these in completely isolated systems. So sometimes there are other reactions that take place while the reaction that we want, or that we're focusing on, what we call the system, is doing its thing. Let's think of one example here, gasoline engines. Gasoline engines, you have gasoline that reacts with oxygen. You should get carbon dioxide and water that comes out of there. Well, one thing that occurs during these reactions is not only is the gasoline surrounded by oxygen to burn with, but about 80% of our air is nitrogen. So it's also surrounded by nitrogen. And the oxygen and nitrogen are together. So what this creates is what they call NOx compounds, or NOx, or nitrogen oxide compounds. Let me write on that. NOx. Okay, and that's what they'll call it. And the X there is like a variable that says that, I could have any number there, NO, NO2, N2O5s, maybe. I don't know all of the ones that you can get. But you also get these nitrogen oxide compounds that bond together with the hydrocarbons of the gasoline. And they become side reactions, additional things that we weren't really counting on because we didn't have it in an isolated system where it was just gasoline and oxygen alone all by themselves. So in this case, if you weighed all of the products, and you weren't counting on the nitrogen that was a part of it, you may get additional products there. Sometimes it can be moisture. Moisture can come in a couple of different ways. Maybe if this is in some type of an aqueous solution, it was in water, the reaction took place in water, then water would be a part of that, right? And if you wanted to extract its product, you may get water that comes along with it. Many times we go through separation techniques to try and separate it from the water, or we'll go through drying techniques to try and evaporate away the water, as much of it as we can. And another place that water can get into our product is just through the moisture in the air, because we do generally live in in an environment that has what we call humidity, right? Maybe comfortable humidities might be 30 or 40%. If you live in different regions of the world, it could be much higher as far as what the humidity is. And this dampness will get into the chemicals themselves and will change their mass. So there are a couple of reasons that why we're gaining, or these new molecules are showing up that could give us a yield that is greater than 100%. However, that's rare. Usually, it is a loss that we have. It's kind of like we're losing atoms along the way. Of course, we know we can't lose atoms, really, but they sort of become misplaced, if you will. These can break up into a couple different reasons. One, it might be a processing thing. It's kind of like when you're making frosting to go on a cake or something like that. And if you think about making up that frosting, when you're all done with the cake, you look around, there's frosting everywhere, right? It's on the little scooper thing, it's on the spoon that you mixed with, it's on the tool that you use to spread the frosting out. You have frosting left over in the bowl. You may have some frosting sitting on your nose. You may eat some along the way. So all along the way, all of these little sugar frosting molecules are being lost or misplaced, not in where you want them to end up. And sometimes that's what happens in chemical processes as well, is you can misplace some of the product along the way. Maybe it gets left over in a beaker, maybe it gets washed down the sink, left over on your stirring rod, wherever, spilled on the floor. It can be in many different places that you misplace or lose some of this product, making your yield less than 100%. Another reason is an incomplete reaction. Later, or at some point, you'll learn about the collision theory. Collision theory is how things react. We say that things have to collide effectively in order for them to react. A collision means they actually have to bump into one another. And so we're saying that every atom or every molecule of this reaction has to bump into whatever other atom or molecule that it needs to get the reaction moving along. And many of these reactions involve multiple different steps. So there's not just one bump that has to take place, but there are many collisions that have to take place. And so, what are the chances that not every atom and every molecule is going to find its collision to take place with, so that the reaction doesn't finish? And as you get lower and lower and lower in the amount of reactant that you have left over, as it gets used up and turned into product and less of it left behind, then it becomes more and more difficult for these atoms to run into each other. So just the fact that the reaction just doesn't quite make it to completion. Sometimes it's a time thing. Maybe there's not enough time for it to react completely. And this is the case with automobile engines. Automobile engines, the reaction has to take place very fast. Within hundreds or thousandths of a second, the reaction is over. And so maybe during that time, the reaction just didn't have enough time to completely react everything. Last thing are what we call equilibrium effects. Equilibrium is an idea that in some type of a closed system, meaning if we have it so that we're not taking something out of the system, we're doing it in some type of enclosed vessel, then what happens is the reaction can actually begin going in the reverse direction for many reactions. And so this is kind of like climbing up an escalator when the escalator is going down and you're going up. And let's say, just for a fun idea here, that the higher up on this escalator that's going down, the higher up on this escalator you go, the faster that escalator starts to move in the opposite direction. And then you start to kind of begin to get tired, and so you slow down as you're getting to the top. And eventually, if you can imagine this, you and the escalator might end up going at the same speed in opposite directions. And that's what happens to chemical reactions many times, especially closed ones. You establish what is known as an equilibrium, and that's where the forward and reverse reaction are taking place at the same time in the same speed. And what happens is the reaction never quite gets to the end. So it stops somewhere in the middle as far as the amounts that go there. That might be something for a little later on that you're studying, but maybe not. It's just another reason for some possible losses or some possible incompleteness of the reaction, and turns into yields that are less than 100%. Okay, so let's move on and look at how we might be able to set up and calculate some of these percent yield problems. Over here in the corner, I've put our formula for it, and we're going to go ahead and take a look at a type of problem. Now, when you're setting these up, this is going to be kind of a two-step problem. The first step is we're going to have to do some stoichiometry. Why? We got to find that theoretical yield down here, and so we need to do the stoichiometry because that's where you find that number. And then second of all, then we have to set up this percent yield fraction like we see it here to calculate the percent yield. So two steps that I'm going to go through. Here's our problem. The problem says that lithium nitride reacts with water and it forms ammonia and some lithium hydroxide. So we're going to start off with 25 grams of lithium nitride, and it says you're going to start out with this 25 grams of it. And lithium nitride, we can find that right there. And it says that it's used in the reaction. It says, and 48.5 grams of the lithium hydroxide is produced. That's this over here. There's the product. And it says that 48.5 grams of that's produced. This is a mark of a percent yield problem. So even if it doesn't ask you what is the percent yield problem, this is a mark of a percent yield problem where they give you a reactant and then they give you a product and they say this is how much product was made. You say, well, where's the math that I have to do? I don't have to do anything. This right here, this 48.5 grams, that is our actual yield. Okay, that's the actual yield right there. What we have to do is use stoichiometry to find the theoretical yield over here. All right, and then we'll take and divide those two into each other. So stoichiometry, you should be pretty good at that. Probably. I know that by the time we get to this in my course, my students have already done quite a few stoichiometry problems. If you're finding that you don't know how to set up a stoichiometry problem, I have other videos. I have a mole-to-mole, mole-to-mass, and mass-to-mass stoichiometry videos that you might want to view first before you attempt this. All right, so I'm going to start out with, what do I want to know? I want to know how many grams of the lithium hydroxide can I theoretically produce here? Okay, how many grams of this lithium hydroxide can I theoretically produce? So, and I'm going to say that if I start out with 25 grams of the lithium nitride. So I'm going to set up my stoichiometry. Stoichiometry process, remember, is change it to moles, molar ratio, and then change it back to grams. So the first process is I'm going to take the lithium nitride here, and I'm going to change it to moles. So on the bottom, I'm going to put the grams of the lithium nitride, and on the top, I'm going to put 1 mole of lithium nitride. I put 1 mole of lithium nitride not because it's 1 up here, but because 1 mole of lithium nitride is equal to, get my notes here, 34.7 grams. Now that I'm going to change that to moles, next step is the molar ratio. I'm going to do all 3 of my steps stuck together here so I can conserve a little space. So if this bothers you, do all 3 of them in 3 separate steps then. So down on the bottom, since this is the molar ratio, I know that that's moles over moles. I know it's 2 different substances. The substance I started with was the lithium nitride. And the substance I want to change it to is the lithium hydroxide. The molar ratio is where I make the switch from one substance to another. And these numbers right here come from the balanced chemical equation. These are the coefficients. So a coefficient here for lithium nitride is 1, and for lithium hydroxide is 3. So I'll put the 3 with the lithium hydroxide and the 1 with the nitride. And so I've changed it to moles, molar ratio. Now I'm going to change it back to grams. So on the bottom down here, I'll put 1 mole of the lithium hydroxide. And on the top, I'll put lithium hydroxide's mass, which is 23.9 grams. I'm getting these masses here from the periodic table. When I crunch this through my calculator, I find out that this should equal, this theoretically maximum amount, according to the law of conservation of matter, would be 51.7 grams of the lithium hydroxide. This right here is my theoretical amount. You might want to make a note of that in your notes. That's the theoretical amount. We found it with theory, the theory of stoichiometry, the theory of conservation of matter here is how we figured out what this number is. So theoretically, we should be able to get 51.7 grams if everything was perfect. But check this out. Everything was not perfect, was it? 48.5 grams is what I got. So the next stage to this problem is I need to take my actual yield and divide it by my theoretical yield. This is the ratio that we're looking for. So on the top, as I'm going to put what I actually got, this comes from the problem, the 48.5. And then on the bottom down here, I'm going to put my theoretical amount. That's the 51.7. I'm going to multiply it by 100 so I can make it a percent. Percent means out of 100. And when I do that, I find out that it's 93.8%. How's that? So 2 steps in setting these up. Find the information that's in the problem there, what you're going to start with. That'll be a reactant. And then what is the actual yield? How much actually came from the problem? That will be the product. So find them. Find them in the balanced chemical equation. And then set up your stoichiometry to find the theoretical yield. and divide those two into each other using our new formula for percent yield and determine the yield of that reaction. All right. So as usual, I'm going to give you a shot at one of these. And let me clear off my board here. And I'll pull this one up for you. There you go. And how about you press that pause button and give yourself a couple minutes to do this. And then when you hit play again, I'll be right here to show you how I did it. Go ahead. Okay, how'd you do? There's my work. Wonder if you got 88.3% like I did. I hope so. So let's check this out here. Did my stoichiometry first. Okay, it says that I'm starting with 15 grams of aluminum, so that's what I started with. And I'm going to find out how many grams of aluminum oxide. Theoretically, change it to moles, molar ratio, change it back to grams of aluminum oxide, 28.3. That's my theoretical amount. Now I'm going to set it up with my ratio. 25 grams, that came from the problem. That's the actual amount. They'll tell us what that is because you're not there to see how much it is, so they have to tell you. And then down here is my theoretical amount that I calculated from over there, right? Times 100 to slide that decimal over, and I got 88.3. All right, so here's what we learned. We learned about what percent yield is, how it's a ratio of how much you actually got, how much product you actually got divided by the amount that you theoretically should have gotten. We saw some reasons for why there might be more than 100% and a reason why there might be less than 100%. And then finally, we saw how to set up and calculate these two-step problems, where you first have to do a stoichiometry problem and then throw it into our new percent yield fraction in order to get the answer. All right, hope that went well for you, and I hope to see you again to study some more chemistry.